To end our discussion of organic evolution and its relationship to the taxa that we're studying, dinosaurs, I have a few other little things here. And we're going to start with going back to taxonomy. Remember, that's the naming of things: kingdom, phylum, class, order, family, genus, species. And the way I presented it last time was that it was a nice, simple measure of relationships. But it is not always the most reliable thing because it's based upon overall similarity. And as you can see by the example I give there, that can lead you astray somewhat. So, what do biologists do? If they don't use taxonomy, there's multiple things that they use to study evolutionary relationships, but the modern sort of standard is a science called cladistics. Well beyond the nature of this course, but realize that what it does is it makes diagrams that look like branching trees, and they show evolutionary relationships based upon what morphologies each species or taxon that you're looking at shares with other species. And so we still use taxonomy. It's great for naming things, but to show true branching evolutionary relationships, we use cladistics. Well, let's look at a few examples of characters and sort of how we can use these to get data for cladistics. These are skulls, generic skulls, and the small little dot or hole on the extreme left side of the face here would be the nostril, the nasal passage opening. The large gray hole is the eye orbit, and then the back of the skull is behind it. And among vertebrates, we have three major groups. We have the anapsids, which have no holes back here. We have the synapsids, which have one hole. And incidentally, you and I and all other mammals are synapsids. And then there are diapsids, which includes birds and dinosaurs, and they are the two-holers. Another way to look at this would be in this sort of nested diagram here. You have the large circle being vertebrates. Everything enclosed in that circle is vertebrates. That's every animal with a backbone. Nested as a smaller group within that are the tetrapods. Those would be animals with four limbs, including mammals, reptiles, amphibians, and birds. And then nested within those would be the amniotes. So notice it excludes amphibians like this frog here. These are animals that have a self-contained egg, and then there you see the synapsids, the one-holers, and the diapsids, the two-holers. Now notice that birds and dinosaurs and crocodiles, birds, crocodiles, not shown here as dinosaurs because it's just living organisms, they are united in a group that we call the archosaurs. So now let's look at a cladogram, and here's one of these evolutionary branching groups. You have some ancestral amniote, the first thing that has an amniotic egg. And the first branch goes into synapsids. Those are those one-holers, which become these weirdos here. Don't worry about that so much, but ultimately mammals, including us and this lynx or whatever cat that is over here. And then the sauropsids, basically the lizard-like organisms. Right? That poor name, but it gives an impression of what's going on. We have the anapsids, no holers, that's turtles. And then diapsids, look, it includes a whole suite of things that are extinct. The extinct ones, their white line, their branching doesn't reach all the way to the top. So notice that includes plesiosaurs and ichthyosaurs and pterosaurs, all those Mesozoic large reptiles that people mistake for dinosaurs but aren't dinosaurs, and then dinosaurs proper. And then notice the group that is branching off most closely to dinosaurs are modern birds. Now we're going to end the course talking about this relationship between dinosaurs and birds, but just realize for now that here's this image. Birds are most closely related to dinosaurs. In fact, dinosaurs are ancestral to these birds. Well, let's look at a more detailed cladogram of just the dinosaurs. And when you look at this thing, I'm going to give a brief explanation of how it works. Every one of these little dots, you notice, is placed where there is a branching. So a dot right here at the bottom for dinosaurs, 2 branches. A dot here for this thing called Ornithischia, 2 branches. Each dot is called a node. And then how you interpret this is everything above a node has a particular set of characters that define the node, and everything below it doesn't have it. So for dinosaurs, everything above this node, so all of this here, all of this branching here, is included in what we consider dinosaurs, or the non-bird dinosaurs. Well, what is that? Let's look at some dinosaur characters real quick. This is a theropod dinosaur, and it has a whole bunch of other sort of characteristics that define it, but notice they emphasize down here the ankle, what they call the AM ankle, or advanced mesotarsal ankle. This is shared by all dinosaurs. Doesn't matter whether it's a small theropod like this, or a giant sauropod, or a duck-billed dinosaur, or an armored dinosaur. They have an ankle structure that looks like this, with 2 bones, we call them the astragalus and the calcaneum, lined up relatively parallel to one another between the tibia, fibula, and then the rest of the tarsals. And this is a very strong hinge that allows the dinosaurs to hold or bear great weights and get rather big. So, go back to the cladogram. Everything above this must have the advanced mesotarsal ankle, as well as a bunch of other characters, but that's the big one. Those things at the beginning of the course that I said you thought might be dinosaurs, but they weren't, Dimetrodon, the plesiosaurs, pliosaurs, pterosaurs, crocodiles, they all are excluded. They're below this node because they don't have that ankle. Let's look in detail at the next nodes. And these are based mostly upon structures of the pelvis. And right away we have 2 major groups. So there's a branching. And we have what's called the ornithischian pelvic structure, which literally translates to bird-hipped. And here, it's this upper dinosaur, an upper bone structure here. The ilium is the large upper bone, so it's the largest one up here. And then below it, you have the pubis and the ischium. The pubis is the one that's in the forward part of the body towards the pubes, and the ischium is the one in the back. Well, notice here, the pubis and the ischium are either directly parallel to one another or sometimes even fused together, and they are both directed backwards. This is how these ornithischian hips are defined. There are other dinosaurs that have what we call lizard hips or saurischian, and here you have the same large ilium at the top. The ischium still points backwards, but the pubis points forward. So notice the simple separation between these two. It's the same 3 bones, same 3 bones. You could have dinosaurs that look remarkably like on the outside, but their pelvic structures can be vastly different. Going back to the cladogram, here's the node for Ornithischia. So everything above that has that ornithischian hip structure. Below it, it doesn't have it. So they're still dinosaurs, but they don't have those hips. What do they have? Well, they are defined by this node here, the Saurischian. And everything above that node, those 3 things, have the Saurischian hips. Let's look at a few other ornithischian characters. Never get the idea that these nodes are based upon just one simple little character. They're usually based upon 1 or 2 or a few large ones, and then a whole suite of simpler, smaller, less important ones. So typical ornithischian characters, I should have bolded it or underlined it or something. Of course, the ornithischian pelvis is number 1. But they also are characterized by having a predentary bone. Now, dentary, that's your lower jaw. The predentary is a little bone that would stick out or be attached to the front end of your dentary. They all have it. Also, ossified tendons. Ossified simply means turned into bone. So these are tendons, these normally flexible cartilaginous tissues that have been bonified. They've been turned into bone. And here they're shown on this skeleton as this array of little cross-hatched patterns across the vertebrae and part of the hip area. And it's a way to strengthen and firm up and solidify their skeleton to hold more weight. So ornithischians have these things, saurischians do not. Next few slides are simply explaining again what I've just done, how we can use the cladogram to give a picture of the evolutionary relationships of the diagrams. But an important note here, notice, is that there is no dates on this. This is strictly done by characteristics of the morphology. What are the bones and the teeth telling us? It doesn't say that Ornithischia originated in the Triassic and Saurischia in the Jurassic or anything like that. There's no time implied in this cladogram. Cladograms are simply an arrangement of morphologic characters. It's going to be different from some other trees you're going to see later. Now, we can talk about the origins of dinosaurs by going to that bottom node. The bottom point on the cladogram is the origin, and it points it here. And again, what a cladogram says is that everything above this node, these are organisms where their fossil skeletons have been found to have that particular structure, the AM ankle, as well as a suite of other things. It doesn't say anything about what rock type it was found in, what environment of rock it was found in, what age of the rock it was found in, where it was found. It's just morphology. We're going to use this cladogram over and over and over again. We're about to starting next week, by doing a tour through all of the different dinosaur groups to look at which ones have been given different names, which are in different families, subfamilies, superfamilies. So we're going to use taxonomy. We're also going to talk about stratigraphy and geologic time, but we're going to keep referring back to this cladogram to show their evolutionary relationships. Well, we talked about origins, that bottom dot there, but if we want to really look and study their origins, we can use cladistics, or we can talk about it in a different way. So if we want to know how and where did it occur, what we do, we go around the globe to the oldest places where we know we've found dinosaurs. Remember, we say dinosaurs, their origins are sometime in the Triassic period. That means they've been found in Triassic rocks. And then we go, if we find them at one certain level in Triassic rocks, and those are the oldest, well, you look lower and try to find something older and older and older. When we do this, we get a diagram that looks like this. Now, this is not a cladogram. You see branching on here. You see the little dots in the branches, and it looks similar to the cladogram, but notice it has time over here. This becomes just what we call an evolutionary tree. Now, when we look at this, in every place we've searched for dinosaurs, we find no evidence of dinosaurs anywhere in the early Triassic. In the middle Triassic, we have a whole bunch of what I call the possibles. They're bones, but they're not strictly truly identifiable. They look like large reptile bones, but we don't have the right features to say that these are dinosaurs. And we also have tracks that look like dinosaur tracks. So it's a bunch of possibles. So they probably originated here, but we don't have good records. Then, boom. In the late Triassic, we get the definites. These are things where we definitely can call them dinosaurs. And notice we have both saurischians and ornithischians immediately here in this late Triassic. What that means is that there probably was some earlier proto-dinosaur that was neither saurischian or ornithischian, or was one or the other, and it marks the origin of these things. Again, remember, we are searching diligently around the globe to find earlier dinosaurs, but the first bona fide ones are in this late Triassic. And where do we get them? Well, The oldest dinosaurs on Pangaea. Now I know this is an early Triassic map. I don't have a middle Triassic map, but it wouldn't have looked very different than this. It would still be Pangaea, and the oldest dinosaurs come from South America. Argentina particularly, in a formation called the Ishigualasto Formation in Argentina. And what do we find there then? So here's a couple of dinosaurs. First is Herrerasaurus. It's a theropod, so it's a meat-eating carnivorous dinosaur. We'll cover them later. But there's the actual dates, 227.8 plus or minus 0.3 million years ago. And a pretty good-sized dinosaur. From the tip of the nose to the tip of the tail, you're looking at 3 to 6 meters in length, and it has all of the requisite dinosaur characters. Pretty big dinosaur, but another dinosaur is also abundant there, and this is a much smaller one. It's also a theropod, so also a carnivorous dinosaur. And here's a little artist reconstruction of one looking to get a nice lizard meal here in the upper corner. And these are much smaller. They're only about 1 meter in length from the tip of the nose to the tip of the tail. But they're both found in the same areas in Argentina, and these are the oldest dinosaurs. If we look around the globe for other places, we don't get dinosaurs that are quite as old, but almost. And here in North America, in New Mexico, we have lots of skeletons of a little dinosaur, another little theropod that's called Coelophysis. We have juveniles, adults, and these things, again, they're sort of in between sizes of the Herrerasaurus and the Eoraptor. And we have so many of these things, we can really say a lot about them. So first of all, they're carnivorous. They have saurischian hips. They have good hands. We have good hand fossils for these. They almost exclusively come from river environments of deposition. And they might have some evidence suggesting sexual dimorphism. So you have about 50% of the population that's a little bit larger, longer necks, shorter arms. Those are thought to be perhaps the males, and then the other half would be the females. The big question here is, well, was this some kind of massive death? Because we have, literally over 100 individuals here. Or was this just some accumulation by river processes like we talked about before? Given the nature of this one, it's probably a case of a fluvial accumulation. But we really, really, really can't be sure. The general disarticulate nature would sort of favor that one, but not strictly. In Europe, the oldest dinosaur is this thing called Plateosaurus, found near Trossingen in Germany, and this is a very big dinosaur. Look at this, 5 to 10 meters in length, enormous thing. Unlike all those other early ones I just showed, this one's a big herbivore, so this is a big plant eater. It has some unusual features of its teeth and claws. And look what we have here. Here we have complete skeletons, and quite a few of them. And these ones that are labeled as incompletes, they are almost complete, plus a whole bunch of isolated ones. These are typically found in what we identify as lake deposits, so not fluvial deposits. So here it is more a case of probably a mass death rather than a post-mortem accumulation. Just some interesting things, and I wanted you to see a few of our earliest dinosaurs. If we look at a list of the diversity in the Triassic, in the oldest parts that we find that contain Triassic dinosaurs, so 228 to 221 million years ago, notice we already have, boom, 10 different species. S is species richness or number of different species. We have 10 of them. 8 of them are saurischians, 2 are ornithischians. So it's, trust me folks, it's not that boom, all of a sudden there's saurischians and ornithischians. Rapid origination. They weren't just created then. There has to be some deeper evolutionary history that we haven't captured. And this is what fascinates paleontologists and makes them want to go get more. Most of these things tend to be herbivores, but 3 of them tend to be theropods or carnivores. These are mostly from South America. Then You move a little bit up higher and you start getting the Coelophysis, Plateosaurus, a little bit earlier, a little bit later, excuse me, 221 to 206 million. Notice we have more species. The number of species has increased, and now we have both saurischians and ornithischians, or both saurischians of both types, large sauropods and then these big theropods. But what about ornithischians? Well, a few, perhaps. But most importantly, we see that these things have already expanded across Pangaea, other side of the globe, really, from South America, these things, and now they're up in Europe and in the United States. If you try to explain the previous slide, I know it's a lot of words, but when you look at it, all you need to know is that right at the beginning, boom, we already have a bunch of different species, and they're not just species of very closely related things, they're species of very different things. And then that even increases, and so that drives this search for earlier and earlier and earlier dinosaurs. Okay, back to the cladogram. So remember, down here in the origin area, this is where we're searching for these earliest dinosaurs. But this diagram itself, the cladogram, I'm always going to call it, this is based just on morphology. Now, how we're going to do this in the next few weeks of this course, we're just basically going to ride up these branches. We're going to hit a node, we're going to define what it is, and then talk about individual dinosaurs in the groups. And we're going to start with the ornithischians. There's a much greater diversity of types of organisms here in the ornithischians. One thing though, they are all herbivorous. These are all the plant-eating dinosaurs. Once we finish those, then we'll go up this other branch on the left side to get the saurischians, which also includes some large herbivores, but it does in fact also include these carnivorous theropods, which are ultimately going to be the ancestors to and offer the branches off of to have the birds. But that's for a future course, future lecture in this course, excuse me.